I'm just going to start this up again, this recording. So let's continue to discuss this. So in this case, there's no reason to sort of inspect the context. Second thing is sending a message, and we saw where that occurred here. It was at this point here where we're sending it to a random neighbor. Now, this random neighbor delineation essentially states to whom we want to send it. We could specify a particular agent. So I could say this message is to be sent to, Z, and the message would, go over to Z. But here we're actually giving it some choice. We're saying, hey, send it to one of my neighbors. And neighbors here means spatial neighbors. Alternatively, we could say send it to one of my connections. And it'll be a random underbar connection, in which case it will be sent to one of my topological connections in a network. I could send it to all my neighbors at once, in which case we'll go to all, or I could send it to all of my connections at once. I could also send it to a random person in the entire network, okay? So, in other words, we could send it to an explicitly specified agent, to a reference to a particular agent, Z. I'm going to send it to Z. Or I could send it to an implicitly specified class of agents, okay? Let's take a look at this. So right now, I've sort of abused this model for office hours yesterday, so let me get it back into shape. Pardon me for just a second while I check the values here. 15.1.5, that looks good. I think we're in good shape here. And we're sending this to a random neighbor. So many of you will know and perhaps fondly recall this this sort of situation. Okay. Oh, that's interesting. So there is actually one residual difference. What is that difference here? Actually, so there's two residual differences. One thing is we have average illness duration. I didn't catch this. Average illness duration. It's 15. So that looks fine. Why is this going? Well, it's not really something to worry about for this case. But there is a residual difference here from what was there earlier, and I can't remember. Contact? Oh, okay. It was in the contact here. No, but I changed that back. Oh, yes. Sorry, this was this was originally that. So what we have though here is a situation where they're spreading it to their neighbors within this field here, and it's spreading out like that, right? Now, a few things here. If I change this, so instead of sending it to a random neighbor, I send it to random here. What that would do is, I think that's how it's delineated. Unfortunately, you can't use the autocomplete because of the issue with this somehow being recording. Okay, here it's being sent to a random neighbor in the entire space. Not just to my neighbors just around me, but to a neighbor in the entire space. And what we see, in fact, is a much faster spread of infection. So what I did is, associated with this transition, I changed the implicitly specified class of agents. Instead of sending this to random neighbor, I sent it to random by itself. And that sends it to a random other agent, regardless of where they're located. Now, does that lead to faster or slower spread? It disseminates more quickly. So we can see that actually this has a very significant impact on who I send it to. Alternatively, I could manually figure out which agent I want to send it to based on their distance from me or whatever, and I could send it to a very particular agent based on some algorithm. That's also fine. But in this case, we're sending it to a implicitly declared set of agents. So messages, it turns out, in any logic can be sent in one of two ways. One is via send, and this is asynchronous. And this is scheduled. So in other words, you say, okay, send a message to Z, and Z then gets that message in, and he doesn't have to handle it immediately. He may be in the middle of something, so he can handle it as he sees fits. The alternative is to use something called deliver, the deliver method, in which case the other person has to immediately handle this method. It forces Z to handle it immediately and trigger off of it immediately. The problem is this can risk infinite loops. You can get a sort of deadlock sort of situation. It's not quite deadlock, but where A calls B and B calls A, and you can get this sort of loop. This is asynchronous, and this is the preferred method. So message payloads can often contain valuable information. So, for example, I might send in a message to Z, not only my identity, but I might send information on where he was infected by me, or the situation under which, the context under which he was infected. He might want to save that away in his history. So this is often very, very useful. And basically we could send messages with common payloads very easily, as well as with the object payload, the other type, which is useful. And so one thing we can do here is to make use of these different payloads. The place you specify what to send is right here. So here we're sending this infection message. Let me ask this: does this message in this particular model, does this message matter? Let's suppose I change this from infection to hi or something like that. Does it matter? Does it matter? I'm going to go up here and have a look. Does it matter what that message is? This thing is fired unconditionally. It's not testing the message, not seeing what it's equal to. Now, it does treat it as just an object, and it turns out that that's as good an object as anyone. If I wanted to actually have different things happen on different message receipts, maybe I have one message for HIV infection, one for Hep C infection, then I could test what the message equals to. But right now, I would argue it doesn't matter at all. So I'm going to send this message hi, an ostensibly friendly message, and it's still going to lead to similar behavior, a massive epidemic of highs being sent to people. Okay, so here we have here we have a situation where the details of the message didn't matter, but in general they may matter. And if we want to make use of this information, so we might send information ourselves. It turns out this information is actually available separately. So if we want to make use of that information, where we receive it, we could say, okay, we do it on message equals if this expression is true. But you notice there's also an action here associated with the message. And the action can make use of that message information. So we've seen this sort of thing before when we have implicitly specified parameters. But here, if we go look, there's this little thing here, and it tells us we could use message to refer to the message. So we can refer here to the message and save that information away, or test, if the message equals, or do something here. We could print out the message. So here I could do trace ln of the message, and what should I expect to see then? Can anyone tell me? If I do trace ln, this prints something out on the console, the value of the message. What should I see? Yeah, I should see many highs on the console, right? Hi, hi, hi. That could be a quite useful thing. Whoa, okay. Now we're in bad shape. By contrast, if I had just sent information to myself, I could have printed out information on that. Okay, let's see, I'm just looking at this. I think we'll go over to this, this bit next time. But this receipt of the message has one additional subtlety I'll just comment on right now. If you go to person and you go into the agent tab, you'll notice that there's a thing here that says on message received, and then there's a thing that says forward message too. You can specify here how messages are to be handled. Let me ask this. Why does it not automatically pass it? If you are the builders of any logic, why wouldn't you have, well, here's the state chart, just pass the message to the state chart. Let the state chart deal with it. So when a message is received, it automatically goes to the state chart. Why might that not be flexible enough or general enough to be adequate?
You have an unconditional transition.
Yes.
You might not always want to trigger that unconditional transition.
Good, good. That's right. So you might want to sort of do some pre-processing, as it were, on the message. So that's a good reason. How about another reason? So pre-processing of the message. Maybe certain messages shouldn't matter to that transition. But what's another big reason? Remember I said there's a distinction between how state charts are different than stocks and flows. And I said in stocks and flows, if you want to consider these more comorbidities, these situations where a person has more than one condition, you need to consider all possible combinations of states. Here, how do we do it in an agent-based framework? How do we handle multiple conditions? We would have what? Multiple state charts. Okay. So if you have multiple state charts, why might you want flexibility like this? Why might you want flexibility up front for handling of the message? Because different messages you might want to send to different state charts, right? So if you have a state chart associated with HIV, and a state chart associated with Hep C, and a state chart associated with diabetes, or a state chart associated with obesogenic behavior, or say physical activity levels, the things that influence those, the message that come in, you might want to route them to different situations. So this on message received, you could figure out how you want to deal with particular types of messages. In a model this simple, you don't have to worry about it. It just automatically forwards messages to the state chart. And that's the default. So if you do add a state chart, by default, the things go to the state chart or the single state chart. But if you added multiple state charts, you'd want to be thinking about on message received. If it's this message, send it to this state chart. That message, send it to that state chart. And those state charts would all go off and handle it happily. So I think next time we're going to just add in handling for the messages to our own. Well, gosh, let's just take the tiny bit of time here and do it here, and we'll get closure on this. So minimalist network ABM model. If we have person here, here we're going to send a message to one of our neighbors. So we're going to send infection message to one of our neighbors, and we'll do random underbar connected. I think it's connected. Underbar this, and then so if excuse me, we don't want to do it there. That's not when we get infected. We want to have a self transition, and we want to have this go here. Maybe every one time unit on average, we send a message to a random connection, and then we want to have this guy here be dependent on message arrival. Okay, so we go to the susceptible state, and if we run this, is this going to work? Is this going to work here? Okay, and why not? Good, good. So the final thing we have to do to make this work is to infect an initial person. And there's actually two ways we could do this. One, we could have it when we click on a person, that it infects them. So how would I do that? Where would I put a click handler? We've never seen this before. But what sort of thing would I be clicking on, ladies and gentlemen? I'd be clicking on their oval. Yeah. So if we go to their oval and we go here, there's actually an Onclick event. And so what would I do here? This may sound strange for non-computer scientists, as many of my utterances might, but what would I do here? Yeah, you'd send yourself a message, send message infection to myself, right? And that would start this person being infected, would it not? So watch this. Okay, and then I can go infect that person. Okay, that one died out. Let's see. Hey. Oh, look. Okay. Well, this is interesting. So is it infecting them? Yeah, it's working. In fact, the other thing I could do would be to up front. We could have in the startup code. You call environment. Oh man. It's like send message environment.deliver to random infection. Okay, and there we would have it going. Now right now the rates are too low for it to sort of catch. So I'll up these rates a little bit. They're recovering too quickly, or they're not spreading it fast enough. So I'm going to slow down how quickly they recover. I'll make them recover only after 20 time steps on average. 0.05, 1 over 20, and now I can run this, and now yeah, it started up there, and it's still not gonna spread. But watch this. Okay, now it's spreading. Okay, so the deal is done. What did we do here? We did just a few things. Number one, we added this transition. We had this going at some rate, which I didn't really pay much attention to, but it sent an infection message to random connected. That's the first thing we did. And then we added in something for this transition that said, if I get a message, go between from this state to that state. And that's the second thing we did. The third thing we did, just to start somebody infected, is we inserted a handler, something called a handler, for Onclick on this oval to basically infect myself. This is sending me an infection message when I'm clicked on. And then the fourth thing we do, which wasn't required but sort of was a little bit more automatic, less manual, is the startup code for main. So when main starts, now we deliver to a randomly chosen individual within the environment. I deliver an infection message. Okay, and then now the infection will spread. So that, ladies and gentlemen, is all we have for today. Okay. So I think there was a group that wanted to talk with me after class today, and I think Stephen also wanted to talk with me. And if you could come by at I think I said 4:30 or so, or say 4:35, given the time right now, that would be good. Okay.
Can I ask one quick question?
Sure.
What happens if you have two states that both unconditionally go to different places on message?
Yeah, so that's a good question. I think it will depend on the vagaries of which it schedules first. I've been asked that question before, and I wanted to investigate it. I haven't gotten around to it.
It's just kind of non-deterministic.
I suspect it's non-deterministic, but I have a competing hypothesis that it depends on something that's in fact deterministic. It's just kind of arbitrary. Like, so the question is it truly stochastic, like it with 0.5 probability, or is it just arbitrary? So maybe it depends in the order with which you added those transitions into the model to that state. You know, the first one wins or something like that, always. And I don't know if you played around with it, I'd value that, or I'll try to play around with it. But I think that's an interesting question. I'm not sure which way they would handle it, but it's worth checking out. Because occasionally you do have those race conditions. You know, you have things that happen